Hello and welcome to E233. I'm your instructor, Gregory Myers. In this video, we're going to take a look at an older version of our P5, specifically the one that focuses on the physics demo. And in this video, we're going to take a look at how to do your simple supported beam version 4. Now you'll notice that I have the copy of my P5.c up, which has my main, which is fundamentally our driver. I also have my sample text file and my P5 instructions. This video assumes that you've already done some of the earlier pieces of this project, as well as some of the previous projects that focus on the physics demo. So you'll notice that what's different about this particular function is that it accepts arrays versus singular values, and particularly it accepts a W or an array of weights. I will use the term vector or array interchangeably here. In this particular example, we're focusing only on single dimensional arrays, but basically we are going to pass to it a single dimensional array that has a load or set of loads in it, a length L for the beam, the A, which corresponds to the W in that it is the location of the loads, the R1, which is our reaction forces at P1, and then R2, which is our reaction forces at P2, and then N, which is the variable then that sort of synchronizes all of the arrays or keeps track of the active elements in all of the arrays. Now, as in the earlier videos, we're going to be making these arrays statically, which we're going to do making them too large, and we're only going to use up to n number of elements. So there will be some improvements to be made in this project later on. But let's go ahead and get started with it. We'll start by jumping into the function itself. You'll notice that I have went ahead and finished out my comments, my comment block above the function, particularly giving a description of each one of the input and output variables and so on. And so what we want to do now is we want to take a look at the code itself inside the function. This assumes that we will be passed a valid array for W and for A, and then ultimately we are going to calculate the values for R1 and R2. So we will do some error checking inside of the function, but we're going to be limited in this video as to what we're going to do, and we'll keep it fairly simple. I'll have an additional video that I will post with some tweaks and tricks for this project. But for now, what we're going to do is we're going to focus on just the basics. Let's go ahead and start with the validation. Some of it will be a bit excessive for this particular example. For instance, we want to go ahead and check to see that our W is in fact not null, which is once again very unlikely in this particular example, that our A is in fact not null, our R1 is not null, and our R2. Actually, what we want to do, and let me rewrite this logic right here, we want to check to see if any of these are null. So I'm going to put ORs in here. And if any of these are null, then basically what we want to do is we simply want to prompt the user that says and say that, hey, there's a problem here. And so in this case, we'll have a printf error, please provide valid arrays. Now, once again, it's very unlikely that we're going to run into this scenario in this particular project, but we're sort of looking at this to the future and how we would handle this. And then more importantly, what we want to do is we want to initialize our results rather optimistically here as exit success. And then anytime that we fail at one of our validations, we simply have results equal to exit failure. In other words, no calculations are going to be done, and the calling function will just simply use the return value to determine whether anything was actually done inside the function. Now, we also want to go ahead and check our L and our N. And so with our L, we can just simply check to see that our length is not, in fact, less than or equal to 0. Seems a little bit counterintuitive the way we're going to do this, but in other words, if passes this stage, then we know that our L is positive. But if L is in fact less than or equal to 0, then we simply have a printf that says error, please provide a valid L, followed by a new line, and then more importantly, then our results equal to exit failure. For the N, as in our earlier examples, we said that we would like to have at least 2 points in the array, and you could make the argument that 1 would be satisfactory, but for the discussion for this project, we're going to focus on N having at least 2 elements. And so what we want to do is we want to check to see if N is in fact less than 2. And if it is less than 2, once again, we simply want to provide a message to the user that says, error, please provide a valid N. And what we can do here is we can also include our N max as a criteria. In other words, we want to make sure that they provide a value that is in fact greater than or equal to 2, but also less than our N max, or rather less than or equal to our N max. And so what we can do here is please provide a valid N between 2 and then our N max, which we're just going to plug in as %D, followed by a period or an exclamation point and a new line, whichever you would like to do. And then our N max constant. And once again, in the future video, we're going to take a look at how to do this with non-static arrays. But more importantly, now what we want to do is we want to check to see that our N is in fact less than 2, or not, excuse me, less than 2, or if our N is greater than our N max. Once again, that just assures that we don't accidentally calculate beyond the end of the array. And in both cases, then we simply have results are equal to exit failure. Now, if we've survived all of our preliminary error checking, it's time to get into the calculation. So we're going to have an else here. Now, there are a couple of additional things that we probably want to check. You could argue that there should be no negative values in your weight vector. However, though, I could give you a scenario where the weight vector could have negative loads, for instance, wind loading or uplift, maybe from a tornado or something along those lines would be a calculation that you would want to do. So we could allow for positive and negative values in our W, but we do not want to have negative values in our A. And so in a future video, we are going to further look at our A vector and make sure that there are no negative values in it. But at this point, then let's go ahead and jump into the calculations. This assumes then we have multiple parallel arrays, all with the same number of elements in. So at this point, we need to go ahead and declare a local variable index that we're going to use to iterate through each one of the elements in our parallel arrays. We'll do this using a for loop that starts off at 0, continues up to our N, and then increments by 1. And at this point, the calculations are pretty straightforward. We'll just have our R1, which is going to be controlled by our index. In other words, which element in our R1 vector we're going to assign the value for the calculation for a specific load. So we're going to apply then in this case, the first element, we start at 0, first element of the load at a specific location. And that is going to be dictated then by our A. So we use our formulas then to leverage the length or the total length of the beam minus then the location that the load was placed on. And then ultimately we divide this by L. We do the calculations then for the second load, or rather, excuse me, the second point, not the second load. That's our R2, which is the reaction force at P2. Once again, we apply the load at a given location in our vector, and it is then multiplied by the location of that load, and that is then simply divided by L. I think I've got a few too many parentheses here. You can probably skip this particular parentheses on this one. But then just to be clear on what we're doing here is we apply a load W at a given location in the array at A, which represents where that load is placed. And so we simply go from the start of the beam to the end of the beam, applying a distributed load. Now, the advantage of doing it this way, and we aren't going to cover that in this video, is that you can actually have just different distributions for your load. In this case, we're just doing constant load that's distributed along all of the points, but that is not necessary with this approach. You can have any loading function that you wish to have. Essentially, at this point, we are done with our function. We return results, either exit success or exit failure. And then we've updated then our R1 and R2 arrays or vectors, and then we can leverage them in our main. So let's go ahead and build this one more time, just to make sure that we haven't introduced any errors. And let's go ahead and get started on our main. And we want to look at the branch then that focuses in on calling our beam interactively. We'll start there because that's probably the simplest one. And you want to remember that this one's a little bit different than the earlier ones, particularly our earlier projects, but also our projectile problems, even in this P5, in that we are going to ask the user not for the distributed load, but we're going to ask them for a singular W, and we're going to ask them for the L or length of the beam. And then from that, we're actually going to have to calculate our W load and our A, where each one of the loads are placed. And so in this case, we're going to take their W that they provided and their A, their N that they provided, and convert them into arrays, not singular values this time. And so what we want to do is we want to go up to the top of our main, and we'll go ahead and declare then a couple more variables. And just to be specific here, what we're going to do is we're actually going to declare them. And I'm normally not going to do this, but I'm actually going to use the word array in the name of the variable. And this is just to further emphasize the fact that we are not dealing with singular values. And then we're going to make them far too large. We're going to use our n max. Once again, we're going to come back to this and how we will change this. And then ultimately, we are also going to create a array for our A, and we're going to once again call this one A underscore array. Once again, not the best name here, but hopefully this gets the point across. And while we're at it, we want to go ahead and create our R1. And at this point, we can go ahead and call this one R1 array as well. And then our R2 array. Now, at this point, these are far larger than they need to be. They're also uninitialized. Essentially, each one of the values in these array can be considered junk, in which case what we want to do is we want to come down to where we collect the values from the user. In this case, there's our beam /I. We prompted the user now for the W, the L, and the N. We are going to make no validation here. We're not going to check any of these values. We're going to do that in a later video, but I'm going to put a little note here that we're going to come back to this. And so it's very important in this particular example that we check our W, our L, and our N before passing them to a function. This was important in the earlier examples, but it's even more important now. And why is it more important now? Is because we are using these values to ultimately calculate our W array and our A array, something that we did not do prior to passing the values, or rather the variables, to the functions in the earlier examples. So at this point, what we're going to do is we're simply going to go ahead and use a for loop, and for index equals 0, index less than n. And once again, hopefully you can start to see why it is very important that we validate our input arguments. And what we'd like to do now is we'd like to, inside this for loop, build our W and build our A array. So we'll start with the simpler one of the two. We'll build our W array. We're going to drive it using the index. And at this point, we're just going to make a very simple assumption that we're applying that load W at every element in the array. And essentially what we have is a distributed load, but with a constant value. Now, the A array is a little more challenging in that we have to do a calculation beforehand that could probably justify another temporary variable. In other words, what we want to do is we want to, based on the number of elements n that the user wants to calculate, basically break up the beam length L into segments. And so probably the easiest way to see this is to create one more temporary variable. And it's going to also be a double. And I'm going to call this from A underscore delta. And this A underscore delta is just going to represent then the distance between successive points on the beam where we are going to apply the W. And so we'll come down here real quick and we will make a calculation for A delta, which our A delta is going to be nothing more than the length of the beam divided by n minus 1. And you're probably wondering why the n minus 1 as opposed to just the n. Well, if you want n data points, you're going to need n minus 1 segments, and n minus 1 segments then is used to dictate the size of each one of the segments. Now, truthfully, you could get away without this temporary variable or this local variable A underscore delta. However, it just helps us in understanding then how we calculate our A underscore array. Once again, we're going to use our index. And then what we're going to do is we're going to leverage the fact that C is 0 based, and we're going to start our array off at 0 or index equals to 0, which means that if we do index times our A delta, then basically the 0th element of the A array is 0. Once again, nice little trick that you can employ in C because it's 0 based. You have to do a little bit different in other languages that are 1 based. But fundamentally, then we build our array that dictates the locations where our load is applied. Now, at this point, we are finally ready to go ahead and call our function. In this case, we say results is equal to simple supported beam version 4. We have our W array set to go. We go ahead and pass to it our L. We have our A underscore array. We have our declared but uninitialized R1 and our declared and uninitialized R2, and then our N that sort of drives the whole thing. Now, once again, there's a lot of assumptions made here, specifically that they are valid N and also a valid L. We will come back to that. I've made a little change here, went from R1 to R1 array. And at this point now, we can go ahead and start looking at the output that we want to have, both from our sample text for the table, but also then for our P5 instructions. You'll see that there was a sample output file in the CSV file. So let's go ahead and look first at the sample text for the table. And basically at this point, then just try to mimic this as best as possible. In this particular example, we're going to focus on the format spec of %8.4f. We'll just have some nice printfs here, make the table look nice. And you notice here that I have a nice border for the table. And then ultimately, then we're just going to go through each one of these and apply then the appropriate variable and the appropriate format spec here. So we have our weight in pounds. And you could argue that that could be the total weight. I just would like for you to repeat back to the user what they entered in for the W. And so in this particular case, percent 8.4F followed by a new line. And then that can simply be then the value W that the user originally put in. Now, the second one that we want to have here, of course, is the L, which for this particular example was assumed to be in feet. Once again, percent 8.4F followed by a new line. And then our L, again, print F, our N, which is just simply going to be the number of elements that the user wished to calculate. That's going to be a percent D because it is an integer. And now this is where things get interesting. And I'm going to go ahead and stub these in here. Our R1, which is also going to be in pounds. And we're going to leave this as percent 8.4F followed by a new line. But the problem here is we don't have a singular R1. And so you have to understand what we're actually trying to do. We are distributing the load W at multiple locations. And each one of those locations will have a resultant reaction force R1 that will be put in the R1 array. Likewise for R2, those are not singular values, but instead here for this nice succinct table, we want to have a singular value. In other words, what we want to do is we want to add up all of the reaction forces at R1 and present them to the user in the table as a singular value. And so I'm going to go ahead and put this in here. This is going to give us a warning, but we want to have a singular R1. And likewise, we're going to have a singular R2. Well, what that means is that after we get done running our simple supported beam version 4, we have to calculate or sum up all of the values in the R1 array and the R2 array to get a singular value for R1 and R2. And to do that, we'll come up here to the top. Once again, we'll add a couple more variables, a singular value for R1, a singular value for R2. And then we're going to tweak this just a little bit in that there's no point in us running these calculations if we were not successful in running our simply supported beam. Likewise, you would argue there's no point printing out the table if we didn't actually successfully run our simple supported beam. So the very first thing that we want to do here is we want to check to see if our results were in fact equal to exit success. And if not, there's no point in actually building our table. Matter of fact, you can make a really strong argument that we want to simply provide a prompt back to the user. So something along the lines of printf error failed to run function. And hopefully you can start to see how this is combined with some of the error checking inside of the function. Now we'll go ahead and move our table up to the true branch of the if statement. And then what we'll do is we'll calculate those singular values by using another for loop. And so we'll just simply use our index variable one more time, starting with 0, index less than n, index plus plus. And hopefully at this point, you can start to see the value of our n, especially when it's limited to values less than or equal to n max. And what we'll do outside of our for loop, preferably we should initialize some of these values up here at the top. And so we'll go through, we can go ahead and initialize our R1 equal to 0.0, R2 equal to 0.0. And we should probably go through and think about initializing some of the other singular values as well that we don't use in our calculations immediately, but those two at the very least. And then what we'll do is we'll come down here again, and we'll simply say R1 is equal to R1 plus whatever the value is in the array at a given index. Now, there are fancier ways of doing this in C, but I'm going to go ahead and stick with the longhand notation and do the same thing with our R2 array. And now what you see is we've essentially summed up all of the values in our array and then presented them in our nice little table. This would probably be a great opportunity for us to go and build this and go ahead and test this. And so what we can do is verify that we have a successful build. And then I'm going to go ahead and CD over to my projects folder. And you can see here, I'm in our P5 project. I'm going to CD into the dist folder, debug MinGW. We've already verified that our switches work. So what we can do is we can jump straight into testing this particular function. And so it's going to be p5.exe. We can go ahead and test our /1d or /beam rather, interactive. And we should be prompted to enter in the load. I'm going to go ahead and put in 100. The beam length specify as 10, and then the number of points 11. And you'll see that the W is listed as a singular value here, as in the initial load that we will ultimately distribute at each one of the points. And then the length of the beam, L in feet, is 10. The N is 11, and so on. Just to verify that we are getting accurate results here, we'll go ahead and change our load to 200. Beam length will still leave it 10, and we'll go ahead and increase, or keep the N the same. And then likewise, we can run it one more time, keeping the load constant, length of the beam constant, and then if we just simply increase the number of points, you'll see the effect then of distributing or adding more of the point loads, each one of which are 100 pounds a piece. So at this point, it looks like we've at least got the output table for the command line looking roughly like we have in our sample. Let's go ahead now and focus on the CSV file. CSV file output is going to have all of the values, not only the summed R1 and the R2, but the R1 and R2 that is a result of each one of the point loads. And ultimately, you're wanting to produce then a N rows, where N is the number of calculations the user requested, 6 columns CSV file, where the first column is the index, the second is the W. We are going to repeat the L multiple times, but we want to then show how A progresses from 0 to L, and then the R1 and R2 for each one of the loads. Hopefully, once we see this CSV file, this project or this particular part of the project will make even more sense. And so just like in the earlier examples, what we want to do is we want to go and open our CSV file for writing, and we want to check to make sure that we were successful at it. And so very carefully copy the name here. I'm going to encourage you to go ahead and hard code the name in for this particular project, but we're going to have our output is going to be equal to fopen. And then we're going to open it for writing. And the very first thing that you want to check is to make sure that you were in fact successful at opening the file. And we've got a couple of different ways that we can do this. We can check to see if it's not equal to null, rather the file pointer is not equal to null. And if for whatever reason it did turn out to be null, you simply want to provide an error back to the user, failed to open output file. And this can happen for a number of reasons, not the least of which is that you have the file open in Excel. Now, at this point, then what we want to do is we want to once again simply leverage our for loop, and we'll start off with our index equals to 0, index less than n, index plus plus, and then we're just going to very carefully craft our output into a 6-column output using fprintf. And then always remember to include the output file pointer. And then what we're going to do is we're going to have several % 8.4 Fs. But the first one is going to be the index. And so in this case, it's going to be %D, immediately followed by a comma, no space. Remember, the spaces are for the humans. And then our W is going to be %8.4F, followed by a comma. And we want to have then one for an L, one for our A, one for our R1, and one for an R2. And then for that last comma, you want to remove it, simply replace it with a new line. If you forget to do that, you'll wind up with all of your output all in one long line. And that's going to be a mistake that you will make at least once. It's a pretty common one. At this point, then, what we want to do is we simply want to plug into each one of those placeholders the correct value. And for the first one is going to be the index itself. The second one is going to be the value, not for W, but for W array, and then that particular location in the array. We will have a singular value for L that is just going to be repeated for each row. We follow that up with the A, or the location of that load, respective between 0 to L. Also driven, if you would, by the index. And then lastly, we have our R1 array, not the singular value of R1, but the R1 array, also controlled by the index. And then our R2 array and the index. At this point, then, once you get done with your output, we always want to remember to close your file. Probably the most important line in this particular project is to remember to close your file. We'll go ahead and build it. And now what we'll do is we'll come back to the command line. And just to prove here that I haven't done this already, I'm going to look at the contents of the directory. You'll see there's no output associated with my simple supported beam. I want to go ahead and run this one more time. We're going to stick with some examples that we've already tested. So 100 for the load, 10 for the beam length, and L is the number of points. And if I type in dir again, sure enough, I have a simple supported beam version 4.csv. This is looking pretty promising here that we might have actually finished this part of the project. And sure enough, you'll see that I have 11 rows, 0 through n-1, or rather 0 through n. Our n-1 is the index, and 1 through n, is the row number. And then what we'll do here is we'll go through, you'll see that the first column represents the load applied to each location on the beam from 0 up to 10. L here is our third column, which is simply then just the length of the beam itself. And then we have our R1, which is the reaction force at P1 due to the load being placed directly above it, the load being 100. And you can see as you shift the load down the beam, the contribution to R1, or rather from R1, whichever way you want to look at it, drops, and the contribution from or to R2 increases until you've placed the load squarely at the end of the beam or on top of P2. So the last thing that we need to do for this particular example is very carefully take our code that we have written, including all of our if statements, bring it down to our parametric version with the same caveats here that we need to validate these arguments. We're going to do that in a later video, so don't worry too much about it. Right now, we're going to assume that the user knows what they're doing. And we're going to rerun our p5.exe/beam/parametric. And we've already tested the switches, so we know that part works. We just need to provide the additional arguments. And just for a little bit of variety, I'm going to change this up a little bit. I'm going to go ahead and do 200. And I'm going to specify a beam length of 15. And I'm also going to specify 21 points, just so we see how this would change. And you notice our table changes, but more importantly, so does our file. And so at this point, you can feel reasonably confident after doing a couple more tests that you have completed your P5. You still want to, once again, go back and revisit this and introduce a little more validation on your arguments. But hopefully you found this video useful. As always, if you have any questions, comments, or concerns, don't hesitate to reach out. And thank you for watching.